Welcome to the second AKN002 video, in which we're going to look at some of the behind the scenes electronics. This video will be in two parts. First off, there'll be some slides explaining what's going on, and secondly there'll be some experimental results. The electronics in question is something I call FredBus. So I'll start off by explaining what it is. Well, it's a simple serial data bus between PICAXE chips. It supports up to a maximum of 15 devices, any number of which can be a transmitter. It's important to note that there's no bus master. Anybody that wants to transmit has to gain control of the bus, transmit and then release it. There's a mandatory arbitration process to ensure that only one transmitter can gain control of the bus at any given time. This is most important to avoid bus contention. The PICAXE devices I'm using are the two larger X2s, that's a 28 pin and a 40 pin. These have capability of both transmitting and receiving. And the 14 N2s are also in use, but these are receivers only, they have no transmit capability. I use an external clock to provide a synchronous signal for the X2 devices. Filling in some technical details, it's a 3-wire bus, the first of which is the engage signal. This indicates the status of the bus. This can be either driven low or not driven, in which case an external resistor pulls the line high. The second signal is the strobe. This is dual purpose. It's used first off for the arbitration process and secondly for the acknowledgement by the receiver. It's driven in the same manner as the engage signal. The third signal is the data itself, and this line can be driven both high and low. And it's absolutely vital that only one device drives this at any given time. We'll look next at the protocol. A FredBus cycle can be divided into three main parts. Firstly, the arbitration process, then the data transfer itself, and finally the acknowledgement. The cycle starts when the engage signal is pulled active. This prevents other devices from attempting to gain control of the bus. Immediately after that, the strobe signal is pulled low to indicate the start of the arbitration process. This ends when the last device driving the strobe line releases it. This device will have won arbitration and it is the transmitter. All the other devices are receivers. Data transfer takes place using the serial out and serial in commands. There's a slide on that at the end of the presentation. Having received the last data byte, the receiver acknowledges to the transmitter that it's got them, and this causes the transmitter to do a bit of housekeeping, and then at the end it releases the engaged signal to indicate the end of the cycle. The bus is immediately ready for reuse. Putting in some actual figures, the arbitration process is highly variable. It's going to depend entirely on the addresses of the devices that are attempting to gain control of the bus, and there's going to be a minimum of about 1 millisecond and up to a maximum of about 13 milliseconds. The data transfer is also a variable depending on the amount of data to be transferred. The final part, the acknowledgement and the housekeeping, is fixed at about 3.5 milliseconds. It's impossible to come to a precise figure of what the capacity of this system is because it's the two variables involved. But if I put practical values in, then I'm getting around about 65 messages per second. Next, we'll look at the arbitration process. We'll start with a quick reminder of why we need it. It's impossible to prevent multiple PICAXE devices accessing FredBus at the same time. The protocol has to be able to handle this. And the purpose of arbitration is to determine which of the devices that want to access the bus will be the transmitter. Only one is permitted. To do this, we give each PICAXE chip a unique address. The address itself is in two parts. The first part is the so-called base address, and this is written in the program. and this can be modified by a maximum of 3 input pins. This enables us to have multiple pickaxes running precisely the same software, while each having a unique address. Each of the transmitter chips then produces a pulse whose width is dependent on this address. That's the basic idea of the arbitration. Looking at the example below in some detail now, let's assume that we've got 4 devices and all of them pull the engage signal active at precisely the same time. If they've done that, they will also drive the strobe signal simultaneously at the same time, and each of them will start counting their individual pulse widths. This is the start of the arbitration process, and the first chip will end that at point A when its timer has expired. When this happens, it releases the strobe line and then immediately tests it. Since there are 3 other drivers all pulling it low, the strobe signal remains low, and this indicates to the first device that this has lost the arbitration process. It then releases the engage signal and is free to carry on with other tasks. The same thing happens to the second and third devices as we go past points B and C. So that as we go past point C, there's now only one pickaxe driving the strobe and the engage signals, both of which of course are still low. We reach point D, the timer of the 4th chip expires. This causes it to release the strobe, which it then retests, and this time the signal is high. That tells that this chip is now the transmitter. In the final slide, we're going to look at the data transfer from transmitter to receiver. As previously mentioned, we use the standard serial out and serial in commands. The serial out command is used to send pairs of bytes. That's a single byte qualifier followed by an actual data byte. The first pair to be transferred is a special pair and is the only pair that's guaranteed to be present. The first byte that's sent is the address of the receiver, and this is the qualifier. The second byte that's sent contains 2 separate pieces of information. The upper 4 bits contain the instruction that the receiver is to execute, and the lower 4 bits tells the number of data bytes that are to follow. This will be a number between 0 and 15. And then finally we send the actual data, each byte of which is preceded by the exclamation mark as a qualifier. This is the test board that's used to verify FredBus. I'll go through the details briefly of what's on it. There are 3 40x2 pickaxes, half a dozen 28x2s and 4 14m2s. There's a clock circuitry here providing a stable 8 MHz clock that's fed to all the X2 devices. This device here is a special one. It's a central controller. It's used for starting the test by sending a trigger to each of the other pickaxes, and also for collecting the results from the test. These 2 devices here and these 6 here are all transmitter receivers. They're all running the same program. The 14M2s are purely receivers, and that they also run their own program. Next door I have the original test board, and while this worked perfectly well in terms of testing, the disadvantage it has is that every time I needed to reprogram a pickaxe, I had to power down, take the pickaxe out, plug it into the development board to program it, reprogram it, plug it back into this board, and then repower and start the testing again. It took time. There's a danger of bending pins, and
I very quickly worked out that this is something I'd have to do many hundreds of times in the course of the development of the different test programs. That really was an effort I wasn't prepared to make. So what I did is I added this what I call access circuitry on here, and this is nothing more than a glorified multiplexer demultiplexer that connects the programming to each of the PICAXEs via the selector switch. So now if I want to reprogram a device, I simply select via these switches here the address of whichever chip I want to reprogram and reprogram it. This saves a vast amount of time. We're going to look at some of the detail of one of the tests that's been run. To do so in real time in the video would take far longer than we've got available. It would take probably even several hours. So what I've done is I've captured one test at random, and I've hopefully prepared enough detail to go through it fairly quickly now. Let's see how we get on. On the screen is the test in question, and it's a burst of 127 messages in 1.97 seconds, fraction under 2 seconds. That gives us a message rate of 63.5 messages per second. That's a little bit below the average that I've been seeing on previous tests, but it's not too far away. Even from a cursory glance at the waveform, you can see that the activity isn't constant throughout the test. At the beginning of the test, for example, over here, the messages are coming rapidly one after the other, and there are periods in the middle towards the end of the test where there are quite long periods of time where there's no message being transmitted. That's where, for example, a device has received the message and is processing it before it's ready to transmit again. Unfortunately, I've only got a 2-channel scope, so I can't show more than 2 signals at a time, and the 2 most interesting ones are on the screen, and they're the strobe in yellow, that's active low, normally high, and in pink, purple is the data line, and that is normally 0, active high. This burst was captured at 200 milliseconds per second, so it's taking up pretty much 10 divisions. As I mentioned earlier, a fraction under 2 seconds. Right, let's look at the waveform in more detail. If we go to the beginning of the test, should be about there, and zoom in. Right, actually what I'll do, if I go a little bit beyond and zoom in, we can see the details of the different transmissions. The first transmission starts here. There's the primer pulse, then the data, there's an acknowledge, it's difficult to see but we'll zoom in on that in a bit more detail, and then the end. Then the next transmission starts immediately afterwards. There's the second one, the third, the fourth, the fifth, the sixth, a much shorter seventh, eighth, a longer ninth, and so on. Let's go to the first one. And wind the time base in a bit. And here we can see exactly what a FredBus cycle looks like, or at least in terms of the strobe and data lines. So immediately prior to this, the engage signal would have gone active. Here the strobe goes active, and this is the start of the arbitration. And this primer pulse, as I call it, is about 0.9 milliseconds long. So that identifies it as that chip number 1 is transmitting. Chip number 1 has won the arbitration. Now this in fact is the lowest priority chip, and the reason it's won the arbitration is because it has no competition. This has the smallest amount of data to send, and so it's been able to, from the trigger pulse, it's been able to construct the data to be sent more quickly than its rivals, let's say, and so it's first in the queue. The others are still processing the data from the trigger pulse. After the arbitration, the first data is sent here. This is in fact 2 bytes, or in fact it's not even a byte, it's 9 bits. There's a start pulse and a byte, and then a short gap, and then another start bit and the second byte. As I mentioned in the slides, the first byte being sent is a qualifier, the second byte is the data byte. And then there are 1, 2, 3, 4, 5, 6 data bytes. This here is the acknowledge pulse sent by the receiver, and then there's a final housekeeping period of approximately 3.5 milliseconds, perhaps a little bit more, and then the next cycle starts by another device taking the strobe low. And this particular chip number 1 is transmitting to chip number 2, and the message it's sending is transmit, nothing more than that, simply make a transmission. We skip now to the second message. And we see the same type of waveform. The primer pulse is here. The width of this one is 5.8 milliseconds, and this is the highest priority chip, chip number 8. It sends the address and instruction and the amount of data to follow here, and it follows it with 1, 2, 3, 4, 5, 6, 7 data bytes. The receiver acknowledges, and then the cycle ends just here. And in this one, chip number 8 is transmitting to chip number 1, and it too is sending the message, the instruction, sorry, to chip number 1 to send a message. We're going to jump ahead a bit now to the, where are we, the 6th transmission. 1, 2, 3, 4, 5, 6. Let's put that in the centre of the oscilloscope. That's it there. And in terms of detail, it's exactly the same as the others that have preceded it. The primer pulse here has a width of 4.4 milliseconds. The time base at the moment is on 5 milliseconds in division, so it's just under 1 division. It's got a primer pulse width of 4.4 milliseconds. That tells us this is chip 6 transmitting. It happens to be sending a message to chip number 7, and this is acknowledged. And so far all the 6 messages that have gone have been transmitted in response to receiving the trigger signal from the controller. What happens at the 7th transmission here, we see that the primer pulse is exactly the same as this primer pulse here. So it's the same chip transmitting again, and the reason it's transmitting again is that one of the previous messages has been sent to this device, and the message being sent was transmit, and this is a result of having received that. So it now transmits, and if I check my notes, it is transmitting to chip number 1, and the information it's sending into chip number 1 is to transmit twice. That's one of the 3 options that are available: either transmit, transmit twice, or transmit to a receive only 14N2 device. I'm going to jump a little bit ahead now to transmission number 11. 1, 2, 3, 4, 5, 6, 7, 8. There's 9 just coming into view. 10 and 11. I'll move it to the centre of the screen. There it is, and I'll zoom in a little bit, and this is the one we're talking about here. And we can see that although it starts off quite normally, the finish is quite different from all the others that we've seen so far. And the reason is there's no acknowledge. The receiver hasn't got the message. So what happens here, the transmitter waits for a while to receive the acknowledge. If it doesn't come, the command will eventually time out, and after that period the transmitter will do the usual housekeeping and end the cycle. And what it will then do is attempt to retransmit the same message again.
Here's a screen capture of that transmission. It's the first of the 3 shown on the screen, and you can very clearly see that there's no acknowledgement when comparing it to the other 2. And here, approximately 100 milliseconds later, is the same transmission, this time succeeding. Finally, we'll look at the data that's collected from the test. The test has in fact been running for more than 2 days, I think. It's quite a long period anyway, and it generates data every 100 tests, and the controller reports these to the terminal. You can see the latest figures in front. If we start line 2253, we can see that the accept total is somewhat more than 2.7 million. And what that means is that there's been that number of messages transmitted. Now the reject total is something like 1.1 million. And what this means is that there have been that number of times that some device or other has lost arbitration. It's nothing to do with reject messages. No messages are being rejected. It's simply a measure of how many times one device has beaten one or more other devices in arbitration. The next line is the R-bit error count is 0. This is the most important figure. This shows that there are no errors in arbitration. What that means is that a device that is meant to defeat another device in arbitration has defeated it. This shows that the arbitration is working properly. The multi-TX count is the count of the number of times that more than one transmitter has tried to transmit at the same time. And that also has to be 0, and indeed is. And the good news is that these 2 figures have always been 0. If these aren't 0, then there's something wrong with the interface, and I'd need to redesign it. I talked a bit earlier about messages that weren't acknowledged. This is actually not a worryingly high figure, but it's a surprisingly high figure. If we look at this figure here, we can see that we've completed 41,100 tests. Each test will contain a variable amount of messages. The one we looked at had 127 messages. Most will be substantially shorter than that. But the total number of messages in total is, as I say, somewhat more than 2.7 million over the course of the 2 whatever part days. But there's still a fair number that go unacknowledged. And if I work the percentages out, it's around about 3.3% of all messages. The actual test we looked at had 8 messages that were not acknowledged, and out of 127, that gives a percentage of 6.3%. That is possibly still not worryingly high, but it's something I need to keep in mind. It's not that messages go missing, it's just so that there may be unacceptable delays in getting the message across if it needs to be repeatedly sent. I don't know what the problem is. Possibly timing issues. I need to do more work on it anyway. What is noticeable is that there's only 2 chips that are having messages that don't get acknowledged. These figures here are on a chip by chip basis. So this is chip 1, chip 2, if I can get the cursor right, 3, 4, 5, 6, 7, 8. So what that tells us is that the only 2 chips that are having messages that don't get acknowledged are in fact the 40X2s. All of the 28X2s as receivers, as transmitters, get all their messages through and acknowledged. And further analysis also shows that the receivers, the intended receivers of these failures, are never any of the 14M2 devices. They are most commonly chips with low address numbers. The highest number I've seen is chip number 6. All the others were 2, 3 or 4. So in conclusion of the testing so far, FredBus works. It's pretty reliable. I've got a few messages going astray, but nothing that I can't cope with. Retransmission normally once works fine, sometimes 2 or 3 times. It's robust. It's pretty easy to set up, and most important of all, I can transmit from any chip to any other chip that I want to. That's what I was after, and that's what I got. So at this point, I'm happy.